If you're far back, you won't be able to get home. Yeah.
Good morning, everybody. Oh, morning, everybody. Um, what a wonderful to see a decent crowd the week before AGU. And I assume you're taking a break from preparing your talks and your posters. So thank you for coming. It's a great pleasure for me to introduce to you Bruno Reynard. He's a professor at the Ecole Normale Supérieure in Lyon. He is also director of the lab there. I've had the pleasure of spending a few months in the summer there over the last few years, trying to figure out how subduction zones work. I wasn't able to figure it out, but as you can see from the title, Bruno will tell us all about that. Everything that I missed will be clear in the next 50 minutes. Bruno got his PhD at the Université de Rennes in Normandy, France, and has been in Lyon since the late Pleistocene. So maybe without further ado, Bruno, take it away.
Okay, thank you, Peter, and thank you for inviting me to give this presentation here. So I made this pretty pompous title. It's my bad English. You can blame it on my bad English. The things I want to talk about is how we make experiments to try and understand what is the nature and the deformation of the plate interface in subduction zones. And I wanted just here to give credit to the students, PhD students, and postdoc who have worked with me over the past years on this kind of topic. So when we deal with the plate interface and the parts I'm interested in, I am dealing with pretty shallow stuff. I know there are people who do deep mantle experiments here. I'm going to restrain my area of interest to, let's say, the first 100 kilometers of the subduction. And in that region, what you're looking at is mostly fluid rock interactions because fluids, mostly aqueous fluids, are released by the oceanic plate that is getting dehydrated as it gets heated up into the mantle. And I'm going to separate two regions based on temperature. We have a region below about 700 degrees C, which is the cold four-arc region, in which fluids are mostly aqueous. They can dissolve a little bit of minerals and other species, but they're mostly water rich. From a higher temperature region in which fluids, aqueous fluids can be totally miscible with magmas, and in that region will get melting, and this will ultimately lead to arc volcanism. So the region, the four-arc region, is characterized by low temperatures. This is because it's just the onset of the subduction, but it's also because in order to explain the heat flow data in this region, geodynamicists like Ikuko Wada or Peter, need to put in an ingredient here which says that the plate motion is decoupled along this interface down to a given depth. So this is decoupled from plate motion and convection. So we have a critical wedge of mantle here. And then we can distinguish several types of subductions, of which two end members can be the Tohoku subduction beneath northeastern Japan, and another end member of hot subduction is the Cascadia subduction west of the United States or Northern America. These are different because of the temperature and speed of the incoming slab and age of the incoming slab. And this will determine how far some minerals are stable. In particular, I pointed out here the stability field of a mineral I'll talk a lot about, which is a antigorite, a type of serpentine mineral. So you see that this stability field changes as the thermal state of the subduction changes, and this is inferred to have some influence on the deformation, deformation being a long-term deformation, or also meaning seismicity that is associated with subduction zones. So one of the motivations of the work I'm carrying on is to understand why should these decoupled and how properties of material can explain that. So I do experiments to study that. Another motivation is that fluids and formation of hydrous minerals are involved in the earthquake cycle. So I just show here this picture from this paper by Ley and co-workers, where they distinguish several domains along the subducting plate. And as you go down, you have more and more fluids being released from the subducting plate, and that can travel along the plate interface and are thought to be very important for explaining the generation of a very large earthquake, but also they are involved in what is happening in the deepest part of this region, which has been described as slow seismicity and includes a whole lot of events, low frequency events, episodic tremor and sleep, slow sleep events, etc., which are sort of intermediate between fast seismic activity in the upper level and the kind of ductile deformation you expect when you go down along the slab. And an important point also is that these events are thought to be potential precursor of large megathrust event like the one that occurred in 2011 in the Tohoku region. And just before the day before this magnitude 9 earthquake, there was a swarm of low frequency events, and this can be tracked down to the potential circulation of fluids that feed the bottom of the seismogenic zone and may play an important role into determining the occurrence of very large earthquakes. So what is the context in which all that happens? Well, it's what I call a complex petrological and metamorphical context. I guess everything is complex in nature to a certain degree. And here there's a complexity due to the fact that we think we have some geological analogs to what happens in subduction zone. These are called high-pressure ophiolites. There are bits of former oceanic crust that are uplifted in mountain ranges. So here is an example of a famous ophiolite in the Alps, which is the Mont Viso ophiolite. What characterizes these regions is that we have low temperature, high pressure metamorphism. We have a lot of deformation taking place. And when we want to perform experiments to try and understand what are the properties of rocks in this kind of conditions. Equilibrium experiments, or classical petrological experiments, are difficult to carry out because of the low temperatures. It means the kinetics are slow. You cannot synthesize very big crystals. You cannot make what we usually do in this kind of in high pressure labs. And so they are difficult to carry out, and they also may not always be totally pertinent, because if we are at low temperatures in nature, then we can be easily out of equilibrium. So I do experiments. We may look a little bit strange at first sight, but I have to use natural samples to do those experiments, because often I cannot grow single crystals large enough in the lab. So I do experiments in which I use single crystals, or sometimes rock chips or rock cores. So it means I have all the complexity of the rock that I put in there, or some of the complexity of the rock. And I use these experiments to measure both state properties, like equations of state and elasticity, which I'll talk a little bit about. And also, an important part of my studies in the last years has been studying transport properties, meaning mechanical properties, to try and get rheologies. I've also studied electrical conductivity, but I won't talk about it today. And we started recently to study porosity and try to relate it to permeability to understand fluid circulation. So what are we dealing with in this system? We have a three-layer system. We have the oceanic crust that suffers dehydration on the way into the mantle. It's heated and dehydrated and transformed progressively to what is called blue schist and then eclogites. Then the fluids released from this transformation may percolate through the system and reach the mantle that is above the subducting plate. So this will cause serpentinization above the plate interface, and it makes up minerals called serpentine, which are clay-like magnesium sheet silicates formed by hydration of peridotite. And I've put up here this very simple view of this reaction, which is accurate to within 80% or 90% in most cases. There are some details, mineralogical details, but this is mostly accurate. So we form serpentine by mixing mantle with some 12% of water. And we can make, these minerals are pretty complicated. They can take different forms. There are two main forms. One is called lizardite. It's a continuous sheet phyllosilicate. So we have layers of magnesium octahedra, silicon tetrahedra that are linked together by these OH bonds that involve hydroxyl groups, and you need the water to form these bonds in these minerals. And then it can get more complicated at higher temperatures. So we have this kind of mineral, which is called antigerite. It's basically the same structure, but this structure gets reversed from periodically, and this gives it properties that are somewhat different, especially for the mechanical aspects. And in between those two entities, we have two fluids circulating between two rock bodies that have a different composition, and that means we expect to have what is called metasomatic reactions at the plate interface, which will lead to the formation of nearly monomineralic rocks, which are very particular, which consist of things like chlorite, talc, which are all related structurally to, they're pretty much akin to this lizardite in the sense that they are continuous sheet silicates. So I'll use lizardite also as a sort of a proxy to understand what is going on for these minerals in terms of their mechanical properties. So what kind of evidence do we have of the presence of these minerals in subduction zones? We know they exist on what we think comes from uplifted subduction zones in mountain belts. But do we have evidence for that in active subduction zone? This comes from seismological studies. This is a well-known paper by Bostock and co-workers, where they show that under Cascadia, you can track the transition associated with the continental moho. So this goes from low velocity crust to the high velocity mantle. And you see that you lose this contrast here, and it gets even inverted here. So it means that in that cold wave region, we are forming a new type of rock that has a lower velocity, even lower velocities than the overlying continental crust. And the way to explain that is to say that we have serpentine mineral forming in there. Other detailed studies have shown that on top of the subducting slab, you can see some specific layers with low velocities and also very large anisotropies. So this has been seen in Cascadia and also under Mexico. And these layers are 1 or 2 kilometers thick, maybe, and they are characterized by these very low velocities and very large anisotropies. So what we can try to do to relate it to the serpentinization process is study the elasticity of serpentine minerals. So we did that on the antigorite form, which is thought to be the most common in subduction setting. Again, as I said, we have to use a natural sample. So we use the natural single crystal, and this is about the size of the sample that we've used for several years for doing, we use only one crystal throughout the whole process of making ambient conditions to high pressure measurements. And we did that with the help of Jay Bass in University of Illinois at Urbana-Champaign, using a particular technique, which is Bruno spectroscopy, which uses an inelastic diffusion of light provided by a laser, which allows you to measure speed wave velocities in particular directions of this sample. So we can measure speed velocities in different directions of this single crystal, and from that we get the elastic constant tensor, and then we can recalculate in 3D the wave velocities in all directions of the sample, and we project that on a stereographic projection to get this kind of plots. So on these plots, we can see that here is at the center is the axis that is perpendicular to this layer structure. So you can see that this is where we get the hottest colors, these red colors, which correspond in that case to the lowest velocities. So we have low velocities along this axis, both for VS and VP. And we get very high velocities when we have waves traveling along these sheets. And the velocity contrast is huge. Here we're at about 6 kilometers per second, and we go up to nearly 9 kilometers per second. So it means this kind of mineral is extremely anisotropic and can explain some of the features that we see in subduction zones. So the nice thing is that once we have this elastic constant tensor, we can calculate velocities for isotropic rocks. That means rocks with random orientation of crystals, or from anisotropic aggregates, which correspond to deformed rocks. So starting with the isotopic case, we can build plots like this, where we have chosen here to plot p-wave velocities as a function of density. Actually, we don't really need that axis. It doesn't have much meaning in the, it's just a way to plot the data. And we have here the kind of values we expect for fresh peridotite that is not hydrated, so high velocities and high densities. And this is what we get from our result for this antigorite serpentine. And we have much lower velocities and much lower densities. So from the seismic observation, we can get the velocities and get from that an estimation of the percentage of serpentinization in the mantle wedge. And we see that in cold mantle wedge, we get nearly zero serpentinization. Within error bars, this can be between 0 and 20% or something like that. Whereas in hot subduction mantle wedge, actually in Cascadia mostly, we have low enough velocities so that we can infer nearly complete serpentinization of the mantle wedge. So there is indication that indeed we have serpentinization and that fluids are actually circulating in this kind of system. Now we can also look at deformed rocks. And what we do in deformed rocks, we use a technique called electron backscatter diffraction to measure the orientation of crystals in a given rock. So we have here chosen a foliated, deformed antigorite schist. Actually, this is the same schist from which we took the single crystal we used for the elasticity measurements. From that, we get an orientation map, and the orientation map, no surprise, tells us that the phyllosilicates are aligned along the foliation. And from the statistics of orientation, we can recalculate the elastic tensor of the deformed rock and get the velocities. And we get these fairly blue colors along the foliation, which tells us that we have high velocities along the foliation and low velocities perpendicular to it, which corresponds to this alignment of crystals. This anisotropy is actually huge. It's 40% for VP and 50% for VS. Yes?
How do you do the average?
To the bulk?
You measure single crystal elasticity.
Yes.
Orientation.
Oh, you can do, there are different sort of averages. You can do the Hill-Voigt-Royce. The Hill average seems to give pretty reasonable results when you want to compare it with the measurements that are done on rocks. That would be my answer. And the rarest one is the one you want to use when you compare with the equation of state measurements, because the boundary conditions are stress continuity. Okay, so we have a huge anisotropy. This is for a comparison in peridotites, what is considered highly anisotropic peridotites would give numbers in the range 10 to 15%. And one way to plot this is actually to look at the evolution of speed wave velocities as a function of angle of incidence with respect to the foliation. So here we consider a wave that is traveling along the foliation, so the angle of incidence is 0. And here we are considering a wave that is traveling perpendicular to the foliation. And you see that we have very large velocity changes. For comparison, the green symbols here show what you expect for a peridotite, and here what you expect for a granite, continental crust. So we go from something which has similar velocities as the dry mantle to something that has velocities even lower than that of the continental crust. And the kind of velocities that we get in these regions match pretty well with what has been seen in these very low velocity layers at the top of the slab. So one potential explanation is that these low velocity layers correspond to highly sheared serpentinite layers or similar material. So what we've shown is that in hot subduction, we have a lot of serpentinization going on in the fore-arc mantle. This is much lower in cold subduction zones, but we still probably have some serpentinization taking place close to the plate interface. Here we think we have pretty thick, very deformed layers of serpentine on the top of the slab. And now we can try and think, can we relate this with the fact that we have a cold mantle wedge that is inferred from decoupling from plate motion, which means that we have specific mechanical properties in the stability field of the serpentine, which is shown here by these dashed green lines. So to do that, we try to make some measurements, of the mechanical properties of serpentine. So we did that at APS in Argonne Laboratory in collaboration with Yanbin Wang. We used the D-dia press. I'm not going to go into the details, experimental details. And we tried to study two main minerals, antigerite, which is this structure I've already described, and lizardite, which is this continuous sheet variety of serpentine. And so these are the kind of curves we can build with this experiment. We are straining the sample, so this goes from 0 to 10% here. We are measuring that using the X-ray beam that is provided by the synchrotron, and we can measure the stress from the diffraction patterns. And we see that for this variety, which is stable at high temperatures, relatively high temperatures, we get stresses that are in the range of about 1 gigapascal. The situation is very different when we look at this chap here, which has nearly the same composition, but a different structure. We have crystals for which we see very high yield stress. This goes up to more than 2 gigapascals here, and other crystals that are in other orientations that show very low yield stress of the order of 100 megapascals. And this means that this kind of material has a very high mechanical anisotropy, and actually it behaves like an anisotropic plastic solid. So one way to compile all these experiments is shown here and compare it with the properties of other materials. So we have here in gray what is called commonly Byerlee law, which is what you expect for frictional failure of dry rocks in the lab. We have here in black the results we obtained in antigerite, which range from a bit less than 1 gigapascal to a bit more than 1 gigapascal. And we have here the two sets of results that we got from lizardite, meaning that when we try to deform these samples parallel to the sheets, we get very high stresses. We need to go to very high stresses to actually bend it. Whereas when we try to slide it along the planes, of course, it makes sense. We have much weaker bonds along these planes, and we can do that with much lower differential stresses. And this is backed up by some DFT calculations that we did to model the amount of energy that you need to slide one layer with respect to the other. So we have two classes of material here, the antigerite stuff, which has a plastic behavior that is a bit lower than what you expect for dry rocks, but still pretty high up there. And you have this kind of minerals, if they are aligned, which you expect in foliated rocks, will give fairly low plastic yield stress of the order of a few tens of megapascals. So after that, we can also, after the experiments, look at the kind of deformation mechanisms we we observed, and we do that by looking at the samples by transmission electron microscopy. And we see that these materials have different textures in the end. In antigerite, we can show that we have shear along oblique directions or diagonal directions that correspond to the modulation of this structure. Whereas in the lizardite structure, we have glide along the basal plane, and actually the sample deforms a little bit like an accordion. You get different sectors that are tilted, and you've got kink planes here, and the sample gets kinked on each side of this layer. So we get kink bands in this type of sample. One it means that in this kind of structure, we have very little possible combination of glide systems. And this has a consequence. We do not have enough independent systems to have a continuity of deformation. So at grain boundaries, it means that we have to have other deformation mechanisms, and the most common one that we observe is that we have grain comminution at grain boundaries, and grain size go down to a few tens of nanometers. And then we can compare this kind of observation with deformation features in nature. So when we do that, we can do that only for antigerite because I don't know many occurrence of lizardite, deformed lizardite. We get the kind of features I've shown already, which are these orientation maps. From that, we can infer that we have similar intracrystalline mechanisms as those we observe in the lab. But we never see the same kind of grain size reduction in natural rocks. We have some grain size reduction, but never down to these very low values here. And so it means that grain size reduction is likely balanced by some recrystallization mechanism in nature. And the most likely one under the conditions of the cold mantle wedge is pressure solution at geological timescales. So we tried to study that. And so pressure solution is a phenomenon that is commonly observed in natural high pressure serpentinite. So here, this is a picture I took on the Mont Viso area in the Alps. We have a foliated serpentinite here. The foliation is subvertical. And this is cross-cut by these veins here that appear greenish and are filled by serpentine fibers. So we have opening of fractures that are filled by the same material, basically, that got dissolved from the whole rock and reprecipitated in those veins. So that's an indication of pressure solution. We also have indications of pressure solution at the thin section scale. These are thin sections in serpentines that are folded. And we see here these limits along the fold hinges that correspond to dissolution features. Yes? I think you need some deformation to form it to start with. Even we start to know things because we can see the transition from one serpentinite type to the other, from lizardite type, which is usually isotropic because it formed under oceanic conditions, to this schist that we have here. And if we have low deformation areas, we see more random orientation of the crystals when compared to a neighboring, more deformed shear zone where we have much more alignment of the crystals. So definitely this has to be related to deformation. Well, that's a question you should ask geologists like Simon Wallis, who's around. It's complex, is the short answer. The long answer could last for days, I guess, and would depend on which geologist you are talking to. But we have the mineral paragenesis that tell us that these things formed under relatively high pressure conditions. That's one way to say it. But of course, you can always debate whether this is actually due to uplift or whatever. But this happens. And we have also these crystals here of tremolite, which is an amphibole, calcium-rich amphibole, that are very euhedral. And the only way to produce such euhedral crystals is to crystallize it from a fluid. So we have indication that we have fluid transport and that this is an important phenomenon in these kind of rocks. So then the next question is, can we try to relate deformation, possibly rheology, to measurable things in the lab? And we went into trying and understanding if we could try to estimate porosity and potentially permeability of these rocks under these high pressure conditions. So we built up some experiments that use isotopic tracers. Another motivation for looking at porosity is that models of the earthquake cycle involve having fluid pressure and porosity cycle associated with the deformation cycle. And so these are models that were developed, for example, by Slip and Blampied, where you need to increase the fluid pressure to a value that is close to the hydrostatic pressure so that you can reach at very great depth the yield strength of the rock. And that causes a stress drop just after the earthquake, but also as the rocks get deformed in the fault gouge, you increase the porosity of the fault gouge. And this contributes to reducing the fluid pressure. And then you can have some mechanism like pressure solution by which you decrease the porosity and start the cycle again and again. So one of the motivations is also to understand how we can relate it to shorter scale deformation. So what do we know about permeability of rocks as a function of depth? We have some data on continental crustal rocks that come from the studies of Manning and Ingebrigtsen, which combine hydrological studies and metamorphic rock studies. And these are the compilation of data that they use to fit some law which is either continuous or considers two different regimes in the brittle crust and in the ductile crust, by which we get down to permeabilities of about 10 to the minus 18, 10 to the minus 19 square meters. And there are also some direct measurements of rocks that come from different depths by Shmonoff and co-workers that give values that are essentially similar. But what about the rocks that we have in subduction zone interface? Well, we don't have much constraints. Some of these come from experiments. So there are really low pressure experiments in which a fluid here, liquid nitrogen or gaseous nitrogen, is pushed through a rock sample. And so you measure the flow of this fluid, and from that you can get estimates of the permeability and the porosity. So you can do measurements on serpentinites and gabbros, which was done mainly by the Hiroshima group. And from that you get a range of data that show first a strong reduction of permeability that is due to a compression of the pores in the system, and then they have these small branch here that they consider the high pressure behavior, and they extrapolate it up to 1 gigapascals, and they get essentially very low values with porosities of 10 to the minus 5 and permeabilities of 10 to the minus 24. You have also rather high temperature experiments in which you can reach equilibrium texture where the porosity can be described by only one parameter, which is the wetting angle of the fluid with the mineral. But this kind of temperature range is clearly a range where the phases we're interested in are unstable. So we're stuck right in the middle with a domain of interest which is between those kind of conditions, and we are dealing with very anisotropic minerals that are akin to clay minerals. So we have to find another way to do that. And the way we did that is to do high pressure experiments where we use deuterium diffusion as a tracer to get an idea of the fluid-rock interaction during the experiment. So the idea is to put in a capsule a chip or ideally a core of a natural rock, which will be our sample. We then fill the capsule with a fine powder of the same rock, which gives us two interesting features. We have porosity in which we can put in extra water, but we don't put any kind of water. We put pure deuterated water. And another action of this powder is that when we go to high pressure and high temperature, the fine grain powder will rapidly equilibrate with the fluid. So we end up with a fluid that is deuterated water in equilibrium with a powder that is of the same nature as the rock. So we get a fluid that is in equilibrium with the rock there. And so we put that at high pressure and high temperature for a given period. Then we recover the sample. We can cut it to do SEM images, and we also use another technique, which is Raman spectroscopy, to get mapping of the isotopic composition. So there is no mistake here. I didn't turn over the sample. This is actually what the sample looks like after this kind of experiment, because we have high porosity. There's a lot of deformation taking place, and the sample shape has actually, the aspect ratio has been totally changed. So then we do Raman imaging. We do mapping using a Raman spectrometer. So each of these pixels here corresponds to a Raman spectrum at different places in the sample. So this is 20 microns and 140 microns in length. And we determine the deuterium to hydrogen ratio using the relative intensity of these two groups of bands, which correspond to the hydroxyl groups in the mineral. So we've got very distinct frequencies of vibration for these bands, so they're very easily recognizable. And we use the intensity ratio here to determine the isotopic ratio. And the nice thing about that is that we can map it all over the sample. Here I show an example where we have here actually a lath of antigerite, which is elongated along this map. And we can see areas where we have here in blue color lower concentration of deuterium. So this corresponds to diffusion profiles. So we can get diffusivity. We can model these maps with a diffusion model. We can get the diffusivity of deuterium in the mineral structure from this kind of from this kind of mapping. And we can also start discussing what we see in terms of texture on this kind of map. So here is the same map as I've shown before, and the corresponding SEM image of the surface of the sample. So we have this very large crystal here that has constant crystallographic orientation. So this corresponds to a single crystal, a priori to a single crystal. And we see on the SEM map that we have cracks that crosscut this crystal, but these cracks, they also crosscut the diffusion domains. So it means that these cracks were not active when we were at high pressure and high temperature. So it means that we can use diffusion to distinguish between active and inactive cracks to estimate the porosity of these rocks. We also see that, I said this is a single crystal, but we have actually two diffusion domains in this single crystal. And so there is here a boundary in which there was fluid diffusion during the high pressure stage of the experiment. And we can actually relate this to actual porosity in the mineral. When we look at this area more closely, we start seeing nanoporosity, which can also be seen by transmission electron microscopy. So this very small porosity here, these aligned negative shaped pores in the crystal that correspond probably to former fractures that were healed, actually are active at high pressure during the experiment. So this is the kind of porosity we need to account for in nature. So here is a summary of what happens during the experiments. We show here piston displacement, the pressure, and the temperature. So as we increase the pressure at ambient temperature, we have a lot of piston displacement, which means a lot of the deformation that we see on the capsule actually occurs during the compression, and this may be viewed as a type of very fast deformation akin to what you would have in an earthquake or a slow slip event. Then we increase the temperature, we equilibrate the sample for a given time, and then we quench temperature and decrease pressure. And then there is a little recovery, which means that, again, most of the deformation took place during the compression. We studied three natural rocks, one blue schist that corresponds to what we expect in the oceanic crust, a serpentinite, which would correspond to the hydrated mantle wedge, and a chlorite schist. Chlorite is a clay mineral that is stable down to more than 100 kilometers, and which we assume represent what we could expect as a metasomatic rock at the plate interface. And then we do this mapping of the isotopic exchange. So here are maps of the blue schist, two different experiments at two different temperatures. You see here the outline of the rock chip that we put in the system, and here is the porous powder of the same rock that was put around it and contained deuterated water. So we have a lot of interaction with the fluid in the powder. This is not surprising, and we see that within the rock there was much less interaction, which corresponds to lower porosity. Here the porosity is probably higher than 10%. Here it is much lower. We have some areas where we have higher porosity. And here this is compared with what we get with the same color scale on serpentinite rock. And you see that we're all in the dark blue here. There is much less isotopic exchange. We can enhance to a smaller scale, and we start seeing that we have some interaction in the powder and in some areas of the rock chip, which is here this sort of hemisphere here and straight boundary here. And of course, we can do some more detailed mapping of specific areas. So then we try to go from this exchange isotopic exchange maps to estimating the porosity. So the principle for that is that we set our experimental conditions so that the diffusion profile length is of a few nanometers, which is much lower than the expected distance between two grain boundaries in the system, and lower than the beam size we use for our Raman mapping. So then when we try to understand what's going on in a given pixel in our map, it means that if we have several cracks in this pixel, we will make an average analysis of several diffusion profiles. So we can compute this from the diffusion equation, and we get that basically the deuterium to hydrogen ratio is proportional to the number of grain boundaries of cracks that we have in one given pixel, multiplied by something that depends on the experimental condition that set the diffusion, the diffusivity of deuterium in the mineral and the time that we've set for the experiment, and that boils down to this characteristic diffusion length. So that means we can translate directly this kind of map into grain boundary density, and then we assume some grain boundary thickness to estimate porosity from that. So it means basically that we illuminate the porosity with the isotopic substitution. So this is the results that we get for different rocks, going from the blue schist to the chloride schist, plate interface type material, including two types of serpentinites, one which is, shouldn't be called undeformed, it's actually a very recrystallized serpentinite, and one that shows low temperature deformation features. And so we see that in the blue schist, we get very light colors, which means we have some porosity in these samples. In the chloride schist, it's all very dark. We barely get any isotopic exchange, which means that the porosity in this sample is very low. And interestingly, in the serpentinite, we get large variation between a recrystallized sample and deformed sample, which means that there is some seismogenic potential for creating porosity cycle in this kind of rock. So it's very interesting. We get estimates of the porosity. Ideally, we would like to have the permeability, but this would require to have some fluid pressure gradient in this kind of experiment, which is actually very difficult, if at all feasible. So then we try to estimate the permeability. So I plot here the porosity, which is what we measure in our experiment as a function of permeability. And we anchored our data on some power law relationship that is valid or not, that is very debatable, but is widely used. And people like to put an exponent there, which is equal to 2 in that region and equal to 3 in that region. I think this one is more based on theory than this one, which is based on observations by other people. Anyway, we get an idea of what could be the permeability associated with this kind of porosity. And actually, we get values for the blue schist that are of the order of 1 to 4%, which is pretty consistent with what people estimate from seismic wave velocities in the oceanic crust under Cascadia or Tohoku subduction. We also get that the rocks that are present at the plate interface have permeabilities that are below 10 to the minus 21, so that means they can be considered as totally impermeable rocks, which is what you need to actually maintain overpressure of fluids in the subductive crust in Cascadia, for example. So we get numbers that seem quite reasonable and explain well the geophysical observations. Then we can compare it with the estimates that we have for continental crustal rocks. Here I show again these data by Ingebrigtsen and Manning and Shmonoff and co-workers. You see that our data for oceanic crust and deformed serpentinite lie on this extrapolation, continuous extrapolation of their data, but it's slightly below what we would expect with slightly different assumption on the mechanical behavior. What is also interesting is that chloride schist here is totally impermeable, which we think is due to the fact that this sheet mineral has a very low yield stress, so it will deform during the experiments, and you cannot build any porosity in this kind of rock. And interestingly, serpentinite showed different behavior depending on the fact that it's highly deformed or highly recrystallized, which gives it a seismogenic potential because porosity change from one state to the other. So I think I can leave you with this slide of conclusions. So we have rocks that are fairly porous here in the crust that can explain why we get visible overpressures that can be seen from seismic wave velocities. On top of that, we have rocks that are impermeable that will provide a seal. And now the discussion is about the thickness of that seal. These metasomatic rocks in the field, they're only a few meters to a few tens of meters thick. So that means that this seal is pretty thin and can be broken during very large quakes or during smaller quakes that crosscut the oceanic crust, for example. But now we have an idea of the properties of these rocks, and we can probably do something useful in modeling the fluid percolation within those kind of systems. Thank you for your attention.
Thank you, Bruno.
So when you kind of imagine the water migration,
Yes, this should relate to the permeabilities. This is something I've tried also to constrain from our experiments, but it means here we have a pretty, if we consider this is a metasomatic transition, we have a pretty constant texture. Whereas when we go to this region here, we have something that starts reacting. So we also have a reactive porosity that is being created in this area, and this gives even more complexity to this kind of system. So I'm currently studying what happens when you dehydrate the sample, which opens up porosity. But here, when you hydrate the peridotite, for example, because you are forming a lower density mineral, you expect to have some expansion cracks that open up and that provide some space for the fluid to go. So here I've described only what takes place around here. If you want to describe what takes place above, you have to take into account the kinetics of hydration, which we know more or less from experiments, and also mechanical aspects of it, which we start to have an idea from observation of natural rocks, for example. So yes, we can. There's a lot of complexity and. The kind of resolution, I would say, is a few kilometers. basically what I'm saying. Yeah, it has to grow by diffusion and probably a little bit by deformation, because if you imagine that you have a seal there, you build overpressure, and this will be released by earthquakes, for example. And then you create some porosity, so the cracks induced by the earthquake will cause some deformation over a certain thickness. It may go through different planes that are separated by a few meters. So you can imagine that you can grow a metasomatic sequence from piling up different deformation events and transformation events. Exactly, which is also, there's a seismological observation that may be related to that under Japan. It's a paper by Kawakatsu, where it shows that there's a low velocity layer just on top of the slab in this region here, which corresponds to, would correspond to the destabilization of this serpentine. So it means that here we would get the fluids out of the crust, which also correspond to the point where we stop having this diffuse seismicity in the oceanic crust. And this diffuse seismicity is due to the fact that here the crust has a fluid overpressure because we have an effective seal, and then we lose this seal, and so we lose the fluids, and we don't get any more this diffuse seismicity in the crust. Uh-huh. Yeah. Yes. Mm-hmm. Uh-huh. I agree with you. It's why when I presented the data on the wedge, I first compared it with the isotopic values, because if we consider this is decoupled, there is no deformation in there, so we don't expect much anisotropy, even though there is some isotropy that is observed in some subduction zones, which is this trench parallel anisotropy that was tentatively explained by anisotropy of the mantle wedge. And when I said that the little layers, very low velocity anisotropic layers on top of the slab could be related to serpentine, I was pushing interpretation a bit farther. I mean, there's other ways to explain these low velocities, and with fluids, for example, so they may be related rather to the overpressured crust rather than the deformed areas here. I agree with you that a few tens of meters of even very highly anisotropic material are probably not going to show much on seismic data. Thank you.